Hello there, wind energy students. Dr. John Schrage here, and we're working our way through the 5th module of the class, and at the present time we are attacking a lecture that's called Orographic Forcing. Now, remember, this business of orographic forcing is about a broader chapter that's about local effects, things that are changing the way the wind is blowing in the immediate vicinity of your turbine or your weather observing station or whatever. And we said in the beginning of the chapter that there were going to be 4 types of local effects, like orography, the roughness of the surface in the immediate vicinity of the turbine or whatever, obstacles to the flow, and thermally driven flows, things that are driven by temperature differences at the surface and so on. And so we're going to be working today through most of the part of the chapter that's about orography. We won't get quite through everything in this first lecture about that, but we need a good definition of this word orography. Orography is definitely not a word that people tend to use in their day-to-day life. If I just pull up a define orography in Google, you get that it is the branch of physical geography dealing with mountains, and I don't like that definition whatsoever. It's certainly not the way we use the word orography or orographic in the context of wind power and meteorology and so on. The Glossary of Meteorology gets a little bit closer in that regard. I like their definition that says that it is that branch, it is the nature of a region with respect to its elevated terrain, or that branch of geomorphology that deals with the disposition and character of hills and mountains. In other words, we're talking about the nature of the shape of the surface underneath the flow. And it wouldn't necessarily have to be mountains, it can be hills and things like that as well. These things are going to be affecting the flow because the flow can't go through these things. I mean, the ways in which the flow is going to have to adjust based on the terrain, the orography of a region, can be extremely important, both from a meteorology point of view and from an energy point of view, and can be extremely difficult to explain. Now, I mean, the classic examples of, you Google orography and things like that, and you're going to see pictures like this. Okay, yes, how the flow flows over the Grand Tetons is an extremely complicated problem. On the other hand, I don't think you're going to be setting up a wind farm in the Grand Tetons. I'm guessing the National Park Service would have words with you about that. But that's not really where we're going with this. I mean, hills are an issue too. This happens to be a section of the bluffs in western Iowa. This is somewhere near Little Sioux. I can't remember exactly where this picture is from. But I mean, the flow can't go into this stuff. I mean, the flow has to find some way over or around or these kinds of obstacles. Clearly, these obstacles, just these simple bluffs that are no more than a couple 100 feet high, affect the flow in ways that are relevant to the wind power industry, considering that the wind power industry, I mean, even a 1% increase in the amount of wind that they're able to capture might be the difference between it being a profitable project and operating at a loss. Again, this is also someplace in western Iowa. I can't remember where this picture comes from. But, I mean, look at the complexity of the terrain. Okay? Yeah, it's not the Grand Tetons, but we're not building a wind farm in the Grand Tetons. We are going to build more wind farms in western Iowa. And when we look at this, it's pretty complex terrain. We're going to have to sort out how this is going to work. Now, you're thinking, but wait a minute, haven't we done this before? We spent a whole module of our course learning about forces, and learning how there was an air parcel and it was experiencing a sum of a whole bunch of forces, like the pressure gradient force, the Coriolis force, and whatever else. We did friction and so on as well. And from that we were able to use Newton's second law and say F equals ma and talk about how those forces added up to an acceleration on the air parcel, and that's all lovely, except it doesn't really work all that close to the surface because we have obstacles. It does not matter if your air parcel is experiencing an acceleration that way, and that way is into the side of a cliff, the flow cannot go that way. Okay, the flow cannot go into the ground. The flow is going to have to figure out if it's going to go around the hill or over the hill, or is the hill going to back the flow up and then it stops and so on. There are a lot of options here as to how the flow could adapt to the presence of orography that are complicated and not directly related to this idea of forces. Forces certainly work as an explanation of the flow if it's relatively straightforward, like up in the free atmosphere, far from obstacles to the flow and so on, and maybe over like a very smooth surface, like over the ocean or even a very flat plain. But in general, that's going to be a loser of a way to explain the flow at the kinds of heights that well, it certainly isn't going to be the whole story of the flow at the heights of, say, your wind turbine. And so we're going to need some way of figuring out what the flow is going to do. Now, your book broadly suggests that there's factors that determine what the flow is going to do. I'm going to actually be a little more specific about that. Meteorologists have a number that they can compute at any given time at a given location. It's called the Froude number, FR, the Froude number. And the Froude number will determine how the flow is going to respond to the obstacles to the flow. It is not exactly the same thing, by the way, if your physics teacher used the word Froude number, although it is in fact related. And there is also a term that means the Froude number that is something you learn in like general physics. This is a different number that Froude came up with. This is a Froude number that determines what the flow is going to do when it encounters a mountain range. And the Froude number is written there on the left side of the screen, and there's a number of factors that go into it. One of them is the static stability. Now, there are, as we learned in a previous module, there are a number of ways to quantify the static stability. That is how hard it is to lift and lower air parcels. We learned about word numbers like the environmental lapse rate and so on when we were doing static stability. A more useful way to quantify static stability that we just haven't encountered yet is NBV, the Brunt-Väisälä frequency. We won't worry at this point of the lecture exactly what the Brunt-Väisälä frequency is, other than it is a number that describes the stability of a layer of air. And the bigger the Brunt-Väisälä frequency gets, the more and more stable the air is. So again, we're not going to give you an equation at this moment for the Brunt-Väisälä frequency, but it's just another measure of the stability of air. It has to do with how great the forces are acting to restore an air parcel in a stable environment. But this is not the last time we're going to see the Brunt-Väisälä frequency, so we'll come back to it a different time. It's a measure of stability. The wind speed comes into the Froude number. It is, by the way, we're just writing it as U here, as in the wind speed, not as in the zonal component of the flow. Again, this is a little bit of a little thing that is not making me all that happy about our textbook, is that they kind of get sloppy about that from time to time. The width of the obstacle that we're worrying about matters with regard to the Froude number. That's going to determine what the flow does when it hits this obstacle. So like if we're talking a mountain range, then here is its width, W. Now this is not width as in like how wide it is, like as in the flow is approaching the mountain range. Well, how wide is it? Can I get around it? This is width as in like how far is it till I'm past this obstacle. Okay, so like, you know, the width is in like how far I have to go before I'm past it. And let's see, okay, so those are the three factors that go into the Froude number. Now, you can see, because it's a ratio, it is going to be a dimensionless number. It's going to be just a number. It doesn't have any units or anything like that. There's a whole bunch of these numbers, like the Froude number, the Reynolds number, and Richardson number, and things like that in meteorology. The Froude number is a ratio. And so we need to think about when is the top big and when is the bottom big and so on. Well, if the flow is weak, so the top number, the numerator, is big, and or the bottom is big, like as in the flow is very stable, you're going to get a Froude number that is very, very small. Okay, much smaller than the number 1. Under those conditions, the flow is not going to be able to get over the mountain. The flow is too weak to overcome the stability of the air, which, remember, when the air is stable, it resists rising and sinking motions, because the air will become, you know, like when you lift the air parcel to try to make it go over the mountain, the air becomes more dense than the air around it and it wants to sink back down. So if the Froude number is really small, and the Froude number is something we can compute based on observations and so on, the air won't be able to go over the mountain. It might be able to go around the mountain, like we see in this picture right here, or it might get backed up. The word we use is blocked. The flow won't be able to go over the mountain and will be stuck on one side of the mountain. We'll see examples of that. But no matter what, it can't go over the mountain if the Froude number is very, very small. Now, if the Froude number is 1, or even much bigger than 1, you're going to start getting some really complicated possibilities where the flow can go. If the flow is like 1-ish, it can go over the mountain, and if the Froude number starts getting really big, you start getting these complicated features of the flow, where the flow kind of swirls, or makes wavy motions, or makes rotor motions, and creates cavities in the flow, all of which we're going to learn about in the future lecture in this module, when we start talking about detached flow. Okay? You're going to get all kinds of crazy possibilities if the Froude number gets really big. But again, they're not going to really be features that we're going to tend to see at the height of like a wind turbine or so on. So for now, let's just focus on a narrow subset of these possibilities. The ones where the flow is able to go over the mountain, but it just sort of follows the terrain. Okay? This is going to be for moderate Froude numbers in the vicinity of 1. Okay? Where the flow is just sort of, it is getting over the mountain, but it is not like, doing something crazy, like, swirling around, making cavities and rotor motions and so on. Alright, we're going to work on that first. That will be our most promising lead as to how to figure out these kinds of flow patterns associated with orography. Now, before we move on to part 2 of this lecture, let me just ask a couple quick questions here. Here's question 1. When we say that the flow is being influenced by orography, we're talking about the influence of blank on the flow. A, areas of high pressure and low pressure. B, the friction at the surface of the Earth. C, the wind shear at the top of the boundary layer. Or D, the uneven surface of the Earth. What is of those? I didn't use any of those exact words when I described it earlier. Which of those is the correct way of describing what we mean when we talk about the role of orography on the local flow? Make a choice from those 4 options and get a little feedback before you move on to question 2.